All right, hello everyone, good morning. So today we'll be opening up a new topic. We are already finished with bipolar junction transistors. So I think we've sufficiently covered all the important parts of the analysis and design of BJT amplifiers. So today, introduce a new electronic device called the field effect transistor. So the same with the BJT, which is a bipolar junction transistor. The FET is also a transistor, so field effect transistor. Those are the two uh, major types of transistors when you get BJTs and FETs. So FETs or field effect transistors are historically, short lang historical background, initially conceptualized or proposed in the 1930s. Okay? Only nga time na conceptualize ang such thing as the field effect transistor. Yet at this time, as we've learned previously in chapter 1, wala pa na-invent basically ang semiconductor device. So in the 1930s, this was before the discovery of the semiconductor material. Before discovery of semicon materials like the P-type material and N-type material semiconductor. So his idea were later refined and developed. Materials were not yet available at the time, yet the practical FET was not constructed until the 1950s. So this was the time that the field effect transistors were invented. So nadire sort of schematic on how it should look like. So in terms of physical construction, the physical construction of the FET is totally different from that of the BJT. FET. If we could remember BJT, the physical construction of the BJT is very simple that, di ba? So nga naman na siya. It's just three semiconductor materials sandwiched together. So if we have an NP and BJT, so this is the N-type material, another P-type material as base, and another N-type material. Same with the PNP type of transistors, PNP. And the terminals are connected at each layer. Muling nga itong mga metal contacts. May connected diya, may connected dire. We're connected dito. So this now becomes our collector. This is our emitter. And this is the base. Diba? Remember? So very easy lang ma-visualize ang physical construction sa BJT. So as for the FET, again, the FET is a totally different device from that of the BJT. It's not necessarily an improvement, but in terms of physical construction, yes, it's a different device. FETs come in two flavors, much in the same way that BJTs also come in two flavors, NPN or BNP. Ang FET, we have the N-channel FET and the P-channel FET. So what do we mean by this? So say for example, for the N-channel na FET, N-channel lang sa atong i-blowing. So it's somewhat like this. Basically, what I'm blowing actually is a specific type of FET called the JFET, which I'll explain in further detail later. Unlike the BJT, nga 3 layers siya, the FET only has a single layer. Okay. Single layer lang siya. So if it's made of an N-type material, so it's an N-channel JFET. So if P-type material, P-channel JFET. So N-channel man eh. So this completely is an N-type na material. And asa lugar na connected yung mga LEDs or yung mga contact point. One is connected here that will act as a terminal, and another here. And actually, naman noon tayo gibutang dili nga very small, this is just very small, na P-type material, but it's not like the BJT nga naka-sandwich. No? P-type material. And these are both connected with each other. Ang kaning duha ka P-type material. So connected as la class. So we now have basically nalala sa likod. Okay. So basically, we have also 3 terminals for our device. We'll call this terminal the drain. This one is the source. So medyo easier na ma-imagine na to why kana ang mga gipang decide na names for the terminals. It's a source because it's the source for the electrons, like electron flow or current, and drain because di hapo badalong, no? Maragod gyapog faucet, no, or gripo, diba, na i-source sa water, then asa sa padlong dito sa drain, sa sink. And this one is appropriately named also as the gate. Okay, so when the gate is open, water will flow. When the gate is closed, water will not flow. So medyo appropriately named bilang atong mga terminals. Colorin na lang lamay para malag-show tanawon. Okay, so char. Okay. So much like the faucet na analogy, source because this will be the source of the electrons, and drain because dire mo padulong ang mga electrons. But as you could observe, we did not utilize the electron flow of current sa atong analysis of circuits. We used the conventional current flow. So when we say conventional current flow, opposite siya sa electron flow. Kung actual nga electron flow, dili magid mag-agi ang atong current. So sa atong conventional current flow, downward magina, di ba? Kaya dili mo natin i-connect atong ground. So ang current will flow this way. The same sa BJT. So we'll be following the conventional current flow. So atong current will flow from the drain to the source. We'll call this one, atong lang i-differentiate. We'll call this one ID, current sa drain, and we'll call this one as IS, current sa source. Now, same sa BJT, the question that we should be asking is when will current flow? For the BJT, current will flow from the collector to the emitter if we apply current to the base, remember? So it's quite different for the FET current will flow from the drain to the source. Okay, so from the drain to the source, if voltage, this time voltage is applied to our gate. So if mag-apply tayo voltage right here, so na voltage we call VG, VG or VGS, and not necessarily VGS. If we apply a voltage VG, current will flow from drain to the source. So we have now an idea that field effect transistors, ang naka-differ sa iya sa BJT are not only N-channel, made as N-channel and P-channel, but are also voltage controlled current source. Voltage controlled current source. Okay. So the BJT, contrast na to sa BJT. Versus the BJT, which is a current controlled current source. So, diba? Gamay lang review. This is our BJT. Diba? Current will only flow from the collector to the emitter if current is applied to, the base. Dili siya the same sa FET. So this is a symbol for the FET. Ako lang i-reiterate later. So current will only flow from the drain to the source when voltage, negative na siya. Voltage is applied to the gate. So that's one of the characteristics of our primary characteristics of our FET. It's a voltage controlled current source. What else? And the characteristic of the FET is the device itself, okay? The device itself has a very high input impedance. Okay, so if we measure the resistance across the gate terminal, we obtain a very high value. So what's the effect of this one? Okay, because very high ang resistance at this point, Zi is infinite or approaching infinity at that point, meaning no current will flow. No? Even if we already knew that the controlling variable here or controlling parameter is the voltage, but because of this characteristic, no current will flow inside the gate terminal. So because no current will flow inside the gate terminal, one characteristic of our BJT, of our FET, is that Ig will always be equal to 0 amperes. Okay, so paano gina siya? Yan na ng inherent characteristic. Ig is equal to 0 amperes. Now, just like the BJT, we could formulate a what's called this KCL equation, modeling the device. So supposed to be IG will flow in that direction. So meaning IS is equal to IG plus ID, supposed to be. Okay. Maragod gapog sa BJT, di ba? Sa BJT, IE equals IC plus IB. But dili man ta collector, emitter, and base, we have kuan man, gate, drain, and source. So IS is equal to ID plus IG. But because IG is 0, another characteristic of the BJT is IS will always be equal to ID. Okay? Ralph, yes, my question.
Excuse me, sir. Kanang nadoy mo sulod, sir.
Nakuha na si YOLO, I think. Click na ako.
Sige, sir. Thank you, sir.
Okay. So, napabok ko na miss characteristic. Well, in terms of analysis, these are the most important for us to remember. Okay. The FET is a voltage controlled device. It has a very high input impedance. Ang device niya na high input impedance, but I think yes, it will also follow na ang amplifier itself will also have a high input impedance. IG is 0, so IS is equal to IB. No? So, FETs are more temperature stable. More temperature stable ang FET as compared to the BJT. So, because they are more temperature stable, it doesn't mean na pwede na to siya i-subject of very high temperature good, but it could withstand, no? It could withstand high temperature without having an effect to its operation. Unlike the BJT, remember, the BJT, the beta of the BJT is very dependent to temperature. Pero sa atong analysis, ginagamit nato ginamind ang temperature. No? So, atong gina-assume na ang beta is stable. But we've decided that the voltage divider bias is more is a more stable circuit, such that if we use a transistor or a BJT that has a fluctuating beta due to temperature, okay na lang, no? Alang na lang kay at least the voltage divider could manage fluctuating values of beta. Pero for the FET, FETs are more temperature stable, meaning okay lang na init, dili ra kay maapektuhan niya ang operation. And because they are more temperature stable and could be miniaturized, mas easily ma-miniaturize ang FET. FETs make up our modern integrated circuits microprocessors, computers. So, FET ay ang basic building block to our integrated circuits and microprocessors and computers, and all our modern all that is made up by our modern mga devices. They are made of FETs. Actually, specific kind of FET na, but we'll get on with that later. Because FETs are more temperature stable and they could be made very little, unlike the BJT, which has a limit to how small we could construct a BJT. FETs could be made much smaller. Up until now, no, up until now, they're still making smaller and smaller transistors. So if we hear of that term, ang atong mga cell phones and computers are made of transistors, no? If you could look up sa Google, how many transistors is the Intel Core microprocessor made of? The transistors that it is pertaining to our field effect transistors, not BJTs. So kung tawag sa Google din, how many transistors in Core i5? Core i7 mo nakabutang din. So how many transistors in Core i7 na daw? Mga 3 billion. No? 3 billion transistors. Try to wrap this value up in your heads. No? Grabe ni kadako nga value. So 3 billion transistors. And usa na ba nakagamay ang Core i7 na microprocessor? You could put it, no, within the palm of your hands na may lagi kayo na siya. Microprocessor sulod sa inyong mga laptops at mga computers. But it contains 3 billion transistors. And the transistors that it is referring to is FETs, no, or field effect transistors. So FETs are more in line, no, with how computers should work, not BJTs. Mas need na ang atong mga computers is made of FETs than BJTs. Okay? So, what else pa ba? So, something that I missed. There are three major classifications of FETs. So we have the JFET or junction FET. JFET. We have the MOSFET, metal, oxide, semiconductor, FET, or MOSFET. Actually, this one, all of these are made of this specific type of FET, MOSFET, not JFETs. And we also have MESFET, not very common nowadays, but still existing, metal semiconductor. Semiconductor FET. Not very common in its usage nowadays. So junction FETs are more used as amplifiers, while MOSFETs are more used as switches or switching circuits, for which is the basic building block of computers and microprocessors. Okay, basically, di ba? If we could remember, computers work with ones and zeros, which is just a shorthand for on and off ng mga computers, di ba? 1-0, digital, on-off. So basically, switch naman gina siya ang atong computer. And because MOSFETs are more useful as switches, that's why computers and microprocessors are made up of MOSFETs. While JFETs or junction FETs are more easily used as amplifiers. But that's not to say nga dili pwede gamiton ang JFET as switch or ang MOSFET as amplifier. Pwede gyapon, no? So, ang MOSFET pwede man gyapon na siya mag-act as amplifier or ang JFET as switch. Pwede. Pero mas mag-shine sila sa kanilang mga specific use lang, no? Si JFET as amplifier and si MOSFET as switch. Okay. So, sige, symbol, no? Because we have two types of flavors for our FET, the N channel and the P channel. Maybe I'll just doon lang ako sa tanan, no? So, N channel JFET. This is a symbol for the N channel JFET. Just like the BJT, when we say N, no, N channel ni this time, the BJT na the NPN. For the N channel JFET, the arrow will always flow inward. Nagya po arrow. No? So this is a symbol for our JFET. This is the gate. This is the drain. This is the source. For the P channel JFET, of course, the same ba? But ang arrow is pa gawas. For the MOSFET, ako lang siguro i-shorthand as MOS. So, aside sa, we could make N channel and P channel MOSFET. Ano po tayo, another type of category for MOSFETs. We have the enhancement MOSFET and the depletion MOSFET. So there are many types of FETs basically, unlike sa BJT nga, isa lang yun. So sa MOSFET, we have the depletion type MOSFET, deplete, and the enhancement type MOSFET, enhancement. For the depletion type MOSFET, yeah, ang symbol is igani. Medyo complicated, no? Complicated gawingan. It's the gate, the drain, source. This is for the N channel. For the P channel, depletion MOSFET na siya. Enhancement MOS. So this is the N channel depletion MOSFET. Quite a mouthful. Same naman for the P-type depletion MOSFET. Pagawas lang ang arrow. Gate, source, the drain. For the enhancement, it's complex pa yun. A broken line. Pagkadulingan. Same gap one. So, ng mga symbol. Now, we do not really need to memorize all of it because sa atong analysis of FET amplifiers, we'll only be focusing on the N JFET. Focus ang kadila. Okay. Pareha naman na sila, no? N JFET o P JFET. Dahil lang sila polarity o directions of current. Because the MOSFETs are not very common, skip na natin yung D MOSFET. And for the E MOSFET, of course, we'll only focus on the N-channel E MOSFET. I like to add it, didn't necessarily N-channel, P-channel. N-channel, P-channel day. Pero we'll soon, we'll learn sooner na we have a shorthand for the drawing of the E MOSFET na schematic. No? Okay. Kung kani nga itong gamiton na symbol, tugayan man ta. Tapos magkain siya doing, ay kanang complicated na siya doing. Tapos yung introduce po. No? Basta simple lang ang pag-model sa symbol sa E MOSFET para mas makafocus sa makatagtag more attention sa analysis. I think ianap mo siguro ito. No? For the N MOSFET and for the P MOSFET. Shorthand lang na sila. Pero dili sa this meeting. Okay. So I hope I've sufficiently summarized the important aspects of FETs in general. So we'll go a little further into detail sa analysis of FET circuits, particularly with the JFET or the junction FET. So the JFET is a normally on device. No? So what do we mean when a normally on device? Meaning, if we apply no voltage sa gate, current is flowing. No? So normally on siya. If we do not turn it on, if we do not do anything to the gate terminal, current is already flowing from drain to source. That's what we mean when normally on. The N-channel device illustrated when the drain is positive with respect to the source and there is no gate source voltage, there is current in the channel. So even if there is no gate source voltage, there is current in the channel. So that's what we mean when we say normally on. When the negative gate voltage is applied to the FET, the electric field causes the channel to narrow, which in turn causes current to decrease. So opposite siya. If we apply a negative voltage sa gate, we apply a negative voltage here, that's the time na mag-slowly o disappear ang atong current from drain to source. So that's how, basically, that's how JFETs work. Kung ato lang i-simplify yung operation, this is it. So as in the base of the bipolar junction transistor, there are two types of JFETs. Of course, the N-channel and P-channel, I introduced that earlier. The symbol for the N-channel JFET is shown along with the proper polarities of the applied DC voltage. So this is the characteristic curve of JFET. Okay? Characteristic curve. Sige, graph ani. VDS versus ID. Okay? So where will we find that sa atong JFET? to ID. So this is ID, the current from drain to source. And if I remember earlier, ID is equal to IS. So ID versus VDS. So VDS is just the same sa VCE, sa BJT. So natin si VDS, the voltage across the drain to source terminals. So this characteristic curve is obtained when VGS is 0. Again, when VGS is 0, current is flowing from source to drain. So there is the availability of this current when VGS is 0. So we have 3 parts to our characteristic curve. We have the ohmic region, this one, from A to B. This is when at specific values below pinch off, ang voltage to current na characteristics atong FET is much like a resistor, very linear, diba? Remember, the characteristic of a resistor is linear, yung VI na curve for the resistor, it's linear. So much like the FET in the ohmic region. That's why ohmic ang tawag saya because much like resistor. But that's not of interest to us. What is of interest is the voltage above pinch off. So when pinch off is obtained, so try to think of this one as synonymous lang, not exactly, because voltage mo na itong giisgutan. This is synonymous to saturation current of the BJT. So when pinch off is reached, or VP, that's the pinch off voltage. When pinch off is reached, the value of the current flowing from the drain to the source will plateau in value. So mag-constant na siya. And that value is IDSS. So IDSS actually is not only synonymous, but it is the saturation current. So IDSS is the saturation current. Notice, no matter how large the value of VDS is, let's say for example, VDS at pinch off is 2 volts or negative 2 volts, let's say, and maabot siya o 15 volts. It doesn't matter. It doesn't matter that VDS is as low as negative 2 or as high as 15. The value of the current will be the same. So what value is that? That is IDSS. So mahulog na si VP is the condition at which saturation will happen. So there's no such thing man as a saturation voltage, saturation current lang. But VP is the condition where saturation will happen. And we should not worry sa analysis because VP and IDSS are always given. Naman nasa specs. No? Another term for VP is when VGS is off. Sila ang gamitin ng term ba? Later, sa mga formula pa sila ang gamitin ng term. So when VGS is off, that value is VP. Okay? Of course, anything above this value, C, is the breakdown region. The FET, the FET will be busted. So this is another way to look at or is another perspective of a characteristic curve of the JFET. This is for different values of VGS. So depende sa amount of VGS that we apply to the gate terminal, we'll just pick any of this one. So let's say, for example, we pick our VGS as -1. So this is our characteristic curve. We'll use this one and we will ignore all the others. No? Di natin gamiton, di natin gamiton. Again, we'll only just pick any one of this. Isa lang ani. And that value will be the value of the VGS of our circuit. So if we chose one of this, no, pili lang tag isa, that will now be our new characteristic curve, this one. So this is just the characteristic curve when VGS is 0. Lahi po ng characteristic curve when VGS is -1. Pero similar lang sa itsura. Yan ang itsura niya. Notice that VP is constant all throughout. VP is constant all throughout, no matter unsa ang atong use na VGS. But IDSS will change. So IDSS is dependent sa value sa VGS. So if we have a smaller VGS, larger VGS, we also have a large IDSS. So this characteristic curve is VGS versus ID. Previously, kung naman to, VDS versus ID. This one is VGS versus ID. And sa left side siya sa graph, sa Cartesian plane. Negative VGS over ID. Here, this is important because through this graph, we'll be able to solve for the formula or obtain the formula for ID. So mathematicians has already come up with the formula, and it's this one. So sa BJT class, we've memorized multiple formulas, right? Aside sa formulas na naka-locate sa table, we've only memorized at least mga 4 naman siguro ka formula. VBE is 0.7, IE equals IC plus IB, IE is beta to son IB, no? Those formulas, apat nito sa kabuok. Napay isa, RE is 26 millivolts over IE. For the FET, or at least for the JFET, this is the only formula that we're going to memorize. How to solve for ID. So ID could not be readily obtained using the circuit alone. So we need to solve for it. So ID is equal to IDSS quantity 1 minus VGS over VP squared. So kaning VS of this is equivalent to VP. That's mo kayo, VGS of and VP are the same. So this is called the Shockley equation, developed by, I think, William Shockley, together with his team. Shockley equation. So try to memorize lang this one, or at least try to take note of asa siya makita sa itong slide. It's naman yung slide number, but yeah. Take note of this one. ID is equal to IDSS 1 minus VGS over VP. Quantity squared. So IDSS is given. VP is given. VGS could be obtained from the circuit. Now, if na si VGS, we could solve for ID. Or the other way around, pwede. We could solve for VGS if ID is given. So either way, fairly easy naman pag-solve ani. Nalay complication gamay compared to the BJT, pero later na lang. So na siya nga complication. Basta kaya ang point is, if there's one formula that we should memorize, it's this one. And only this one. Okay? Shockley equation. Skip na lang ako ng example. Okay, so we also have another parameter that is very useful to us in analyzing JFET amplifiers already. So the transconductance is important in the analysis of JFET amplifiers. Okay. So I think we derived the Gyapone from the Shockley equation. We have this variable GM, the transconductance. So the transconductance is the ratio of the change in output current ID to the change in input voltage VGS. So that is GM. So GM is equal to delta ID over delta VGS. Or the following approximate formula is useful for calculating GM if you know GMO. So GM is equal to GMO 1 minus VGS over VP. Notice similar na ilahang itsura sa kuan sa Shockley equation. So where is GMO? It's this one. So GMO is 2 times IDSS over absolute value of VP. Again, kani sila, mga VP na sila. VP. VGS off is equal to VP. So ato ning i-synthesize, GM is equal to 2 IDSS over absolute value sa VP, 1 minus VGS over VP. Given. By this time, na-solve na si VGS. So GM is obtainable. Transconductance. Okay. Self-biasing is a type of amplifier configuration for the JFET. Yang equivalent ani sa BJT is the emitter bias. So the self-bias is a simple and effective, so it is the most common biasing method for JFET. With self-bias, the gate is essentially at 0 volts. So self-bias again is the equivalent of the JFET for the emitter bias of the BJT. Solve na later, Ana. Skip na sa ako. Pwede ganit voltage divider. Voltage divider bias is a combination of voltage divider and a source resistor to keep the source more positive than the gate. Stable Gyapone. Voltage divider bias helps stabilize the bias for variations between transistors. So similar, no? Kaya lagi ng itsura. Notice that the source for our JFET amplifier circuit is now VDD, dili na VCC. So VDD na because it is connected to the drain resistor, VDD. Learning biasing. Okay, I think pwede na siya ma-skip. So we have the D MOSFET and the E MOSFET. Ano yung actual physical construction of the E MOSFET? Technically, the gate is not touching the semiconductor material because of the presence of silicon oxide. Metal oxide semiconductor. That's why MOSFET ang tawag. SiO2. The metal oxide semiconductor. So it's the D MOSFET. A symbol. I think I've already introduced this one earlier. Ano siya break din. Disconnected na sila. So, wala kayo kung go into much detail sa D MOSFET because again, it's not really very common for us to use D MOSFET in practice. Only JFET no, for amplifiers, and MOSFETs for switching circuits. Lastly, what if we'll try to use the E MOSFET for amplifiers? No? So E MOSFETs can be biased using bias methods like the BJT methods studied earlier. So pareha, almost similarly kaayo ang pag-analyze sa MOSFET FET circuits, whether JFET or MOSFET. Dahil na kayo pag-analyze because it's very similar to the BJT. Okay. So we'll try to solve at least one example for the DC biasing of JFET. And maybe next meeting, we'll try to compare the total DC and AC analysis of JFETs with that of BJT. So ako lang i-emphasize this morning on how to obtain for ID and BGS for JFETs. Because again, as I said earlier, medyo complicated gamay, no? Complex. Mag-involve siya o quadratic equation. So, kasi makaingon mo nga, quadratic equation, kaya naman. So yes, kaya lang yun. So doon tag-isa. Self-bias. Okay, so how about this one? Figure 7.8. This one. So ako lang ni-rewrite siguro. So solve ID and ID and VGS. Kanila lang. Sorry, kanila lagi. So 18, 1.5, 751. Okay. So, muna yung mga given na daan, guys. Ang IDSS and VP. Okay. So, this is our self-bias circuit of a JFET amplifier. So, we'll just solve for ID and VGS. So, we'll not derive anymore the formulas for the FET. So, talking about before, just refer to the summary table. So, ang FET, lagyan po yung summary table. So, we have different configurations for the JFET. Lagyan po ng fixed bias. Observe. We still have the fixed bias for the example that we're going to solve today. That we're going to solve today, the self-bias, the voltage divider. We have the common gate. This is when RD is equal to 0. Special cases. But anyway, much like what I promised previously, we'll only focus with the three most common configurations: the fixed bias, the self-bias, and the voltage divider bias. So na yung mga formula. Di ito mag-focus on graphical solution, no? Because we'll obtain a very inaccurate nga value. Okay, wala man tayo graphing paper and we have no actual characteristic curve to use. No? So, di tayo focus dyan. So, we'll only use the pertinent equations. So, of these three, for this example, we'll use this one. So, no? VGS is equal to negative ID times RS. And VDS is equal to VDD minus ID RD plus RS. So, sa mga given direct class. VDD is given. RS is given. RS, RD is given. So, once ID is obtained and VG is, once ID is obtained, VG will be solved. And VDS is also solved. So, dali ra. The same gyapon sa BJT. It's just a matter of locating sa summary table o sa formula ito gamiton. So, kani. So, I'll just take note of this one. So, VGS is equal to negative ID RS. So, from the table, so ito, VGS is equal to negative ID RS. So, gamay lang siguro nga kung note kung ato gi-obtain. So, much like the BJT, kanang nga mga formula, tanan formula sa summary table, gipang-obtain na gyapon using KVL. So, kung mag-KVL ta dire, mo to nga formula to makuha actually. Ano to ha? KVL ta diha. Okay. So, IGRG minus VGS minus ISRS is equal to 0. But we know from the characteristic of our FET that IG is 0. And IS is equal to ID. Transposing VGS to the other side, VGS now is equal to negative ID RS. Hence, this formula from the table. So, tanan gyud to, ipang-derive gyud to tanan kay gamit KVL. Pero para din ito sa i-derive, again, much like sa BJT, mag-refer lang sa table. So VGS is equal to negative IDRS. This is equation 1. I'm sorry. Okay. This is equation 1. What is equation 2? Shockley equation. Again, dapat na-memorize na. If not na-memorize, makita ko sa slides. Wala. ID is equal to IDSS 1 minus VGS over VT squared. ID equal to IDSS 1 minus VGS over VP squared. Diba? IDSS 1 minus VGS over VP squared. So, next. So this is equation 2. Actually, so 2 equations, 2 unknowns. Yeah, 2 equations, 2 unknowns. VGS and ID. So what do we do when we have 2 equations, 2 unknowns sa math? Substitute one to the other. So substitute equation 1 to equation 2. It becomes ID is equal to IDSS 1 minus negative IDRS. Over VP squared. Substitute the given formulas from the circuit. Given values, I mean, from the circuit. So IDSS is given. It's 10 milli. 1 plus. I-plus na ako ni class. Para naman sila, no? Minus negative. So, i-plus na ako na. So, 1 plus, what is ID? ID is unknown. What is RS? RS is 750 ohms. 750 ID. VP is, negative na day gapon. Negative man na negative man na si VP. So, negative 4 squared. So, si VP is given. The IDS is given. The circuit RS is also given. So, ang unknown lang yun this time is ID. What's next? Para simple lang sa so far class, ako lang ning own nga simplified nga way. You will not necessarily use this. Okay la. So let ID is equal to X. Para dahil natanawin bitaw mathematically. So this becomes X is equal to 10 milli or kung at least 10 milli. 0.01. 0.01. I-minus na ako ibalik kay negative man si 4. 1 minus what's 750 divided by 4? 187.5. Okay, before I go further, any questions sa akong math? How I perform the math to this one? Okay man akong math, no? Subay pa?
Pero man, sir.
Okay, good. So, at this point, medyo mo ano si algebra, no? Mo take over na siya. So, pagkalimot ang algebra, sige lang. ma-review man sila to while solving this problem. Okay. Expand. Expand this one. I hope kadunong pa mo saan pag-expand o binomial. Mas yung tawag gani. X is equal to 0.01 1 minus ito naman yung FOIL method, di ba? 1 minus 187.5x 1 minus 187.5x FOIL method. So 2 times 187.5 375 minus 375x plus 187.5 squared. 35156.25. X squared. Okay, so ako lang nang i-expand. Nothing fancy pa. Next, we distribute 0.01. So this becomes 0.01 minus 375 times 0.01. 3.75x plus 35,156.25 times 0.01. 351.5625. 51.5625 x squared. Transpose 1 to the other side para madungag anak niya. Okay. So this becomes, in standard position, this becomes 351.5625 x squared minus 4.75x plus 0.01 equal to 0. Quadratic equation. So you have the freedom to use whatever methods you want. You could use your calculators directly, or you could use a quadratic equation, whatever. But that was okay. This is the these are the coefficients. No? But if you're going to use your calculator, don't use shift solve. No, warning dire. For calculators, don't use shift solve. Why? Sa shift solve, isa lang ka-value inyong makuha. Quadratic, we know na ba nga duha ka book value ang magawas dapat. So solving for x, so akong gamiton siguro ang equation nga mode sa calculator. So mode 5, then quadratic man siya. So 3, type na ko ang mga coefficients. 351.5625, negative 4.75, of 0.01. Solving for the values of x using quadratic equation would yield us 10.9 milliamperes. A little lang eh. So duha ka value for our x. So asa kaha sa duha ang atong gamiton?
Greater, sir.
Greater. So ako lang ihatag ang clue. Actually, we have the device characteristics already. IDSS equals to 10 and VP is -4. So if we have an IDSS of 10 milliamperes, remember, when we say IDSS, diba, it's the saturation value, the saturation current, meaning it's already the maximum value. So 10 milliamperes is the saturation current of our device and of our circuit also. So if we obtain 10.9 milliamperes, dili na ni pwede. Nanlapas na ni. No? 10.9 is already, because 10.9
Lower day, sir.
ang lower. Sa kaninga case, no? Sa kaninga case. Because 10.9 is greater than IDSS already. That's why we're not going to use the 10.9. Is greater than IDSS. IDSS should be the maximum saturation current. So the final answer is, therefore, ID is 2.6091 milliamperes. Now, there are also cases, class, there are also cases that both of them are lower than IDSS. So, asa man tong gamiton, sir? What if ang isa dili is 5.2, no? Ang isa is 2.6, ang isa 5.2. So, na next step actually. Swertihan pa dire because the other one is obviously higher than IDSS. So, ato na siyang gi-dismiss. But what if silang duha kay lower? So, we'll proceed to the next step. Substitute it to equation 1. So, substituting to equation 1, ito, VGS is IDRS. RS is 750. So, VGS is negative ID RS. Negative 2.6091 milli times 750. 0.75 kilo. .96. So sa CVGS is nasa mga negative 1.96 volts. And this should also be lower than VP or higher. I guess in this case, negative man. So ilang absolute values is lower. So this should be higher than VP also. So because VP is the pinch off voltage, no? Maximum value na gyapon should be higher than VP. So VGS of a negative 1.96 is higher than VP. So again, if we have obtained two smaller values for ID, we'll substitute them both to equation 1. And for sure, nagyo isa na class, no? Nagyo isa ng amulapas of value. So in this case, isa lang kita conclude. Isa lang ka value ang atong magamit. Dili duha. Okay? Any questions? Understandable ba ang math ani, no?
Yes, sir.
Okay, thank you sa response, James. So, katulang class, no? Mo lang ni ang nadungag na complication, no? With solving the DC parameters for the JFET. Pag-involve yun ni Fermi o quadratic equation, no? Not to worry sa all the other na formulas because it's already laid out here. Ano mo dito? Napaday tayo isang kulang si VDS today. Solve na natin eh. Anyway, given naman tanan. So VDS is equal to VDD minus ID RD plus RS. VDS is equal to VDD minus ID RD plus RS. Did I need VDS only? VDS dapat mo. Solving for VDD, VDS is equal to VDD minus ID RD plus RS. So, wala siya gikuha. For sure, obtained to siya by KBL here. No? So, VDD minus ID RD minus VDS minus ISRS. But because ID is equal to IS, pwede naman tampo si RD o RS. Ano naman dito nun? No, given naman eh. VDD is 18 minus ID is 2.6091 milli. RD is 1.5 kilo. RS is 750 ohms or 0.75 kilo. Para dali na siya ma-add. So 18 minus 2.6091 times 1.5 plus 1.75. 12.13. So mga 12.13 volts. And I think I'd agree nga, fairly understandable naman. No? As long as given tanan, dali lagi na siya ma-solve.